Okay, so we're going to continue this session, starting by thinking about incentive-aware learning and Stackelberg security games, and in general, repeated Stackelberg games. Again, as before, if you have any questions, please use the Q&A or the chat, and I will stop to address some of the bigger questions, but as we go. So I'm going to start talking about Stackelberg security games, which are a special type of Stackelberg games. Their main special feature is that the utility in them is linear. Let's understand them slightly more. The Stackelberg security games, you can think about it as interaction between a defender and attacker. And this is the picture that Chara also was talking about yesterday. So let's just dig into it a little bit more. The leader is taking the role of a defender, and that's also the role of the learner when you're trying to learn about an attacker. And the follower is the attacker. You can think about it as having n targets, and for example, gorillas and elephants here. And the defender has some resources that he can use to protect these targets. For example, maybe it has, one vehicle that can at one time or the others be around the area that elephants or gorillas would be being poached. Then when the defender is using these resources, he could be using them in a randomized way. So for example, with some probability, it can be present in the west of this continent and with some probability on the right. The set of all valid coverage probabilities, these are, with probability what each of these targets is being covered, is just some set P that is defined by the resources that the defender has and how these resources can be used to actually protect these targets. Now, when the defender is actually protecting these targets, the defender and attacker both receive payoffs based on what is the probability that the target is being protected and which target is being attacked. And both of these are basically the expected payoff that if an attacker attacks one of these animals, how much utility is going to draw from them. I have the example that we are using. I have the game table down here that we can take a look at, but sort of at a high level, it has two targets, gorillas and elephants. And gorillas, if a gorilla is being attacked, I'm going to, and I'm not there to protect it, I'm going to have a loss of 4. This is because gorillas are on the verge of extinction, and it's really bad if I lose one of them. And the attacker is gaining a utility of 2 from a successful attack. I also have elephants, where if I lose one, it's definitely a tragedy, but elephants are not as extinct on the path of extinction as gorillas are. And they're also more valuable to the attackers because they have these valuable ivory tusks. So if they're successfully attacked, the attacker will receive a utility of 4 out of them. So there's a mismatch between the utilities of the defender and the attacker. Now, what is the optimal policy here? So optimal policy, in fact, one policy is that the defender will split its one resource to spend 1/3 of the time protecting the gorillas and 2/3 of the time protecting the elephants. Now, what does the attacker payoff look like here? If the attacker were to attack gorillas, it will succeed with probability 2/3, because I wasn't there with probability 2/3, and will draw a utility of 2. So the utility in expectation is just 4/3. Condition on also trying to attack elephants, I'm not there to protect the elephants 1/3 of the time. For a much higher utility, they're going to draw 4. So in fact, these two are more or less equal to each other, especially if you just change a little bit, how much probability you're protecting the gorillas versus the elephants, the attacker would rather attack the elephants. Now, what is the utility of the defender? When I define the best response by the elephant, I wasn't there to protect them 1/3 of the time. And for that 1/3 of the time, I'm getting a utility of -2. So the defender's utility is -2/3. Now, the tricky thing about these Stackelberg games is that even if I know my utility, but I don't know the attacker's utility, I don't quite know how to design a good strategy. So let's say that I was a little bit off actually, and I misestimated these parameters. And in fact, both gorillas and elephants were valued equally by attackers at 3 and 3. In that case, when I present this, 1/3, 2/3 protection plan, the attackers would prefer to attack gorillas now. And I will end up with a utility that is much worse because I wasn't there to protect the gorillas with a higher probability of 2/3, and I did lose at a higher rate of -4. So as you see, it's really important to know exactly what is the utility of the attacker if we are trying to design good policies in Stackelberg games. And what's kind of these are special types of Stackelberg games in the sense that the utility of both the attacker and the defender is linear in the coverage of the targets, given once we fix the target that's being attacked. Okay, so how do we actually, if we don't know these attacker utilities, how can we overcome them? Before I address that, I actually want to tell you how would you even come up with a good optimal strategy like what I did in the last slide if you knew everything, if you knew the full game table. It's actually instructive to think about it a little bit more. When I know all the payoffs, it's basically as if I'm solving multiple linear programs. Why? This is the space of all probability coverage vectors that I could be protecting the gorillas and elephants, and it's divided to 2 regions. These are strategies or probability vectors that will end up with gorilla being attacked as a best response, and these are the ones where elephant is being attacked as a best response. Now, each of these subregions are defined by constraints over the attacker utility, as in all of this region, the attacker should be drawing more utility from attacking elephants than attacking gorillas. On the other hand, once I'm in that region, the utility of the defender is just a linear function of the probability vector. It's just conditioned on elephants being attacked, how much am I covering elephants in a way. Okay, so this is for known payoffs. Now, if I don't know the payoffs of the attacker, I don't know the division of this space to elephants and gorillas, but I can still query a region. What does querying a region mean here? It means that I can design a policy and I can see once that policy was in place, which of the 2 animals was attacked. That's one way of thinking about querying or designing an experiment in a way. So maybe I will actually take this probability vector, which is, I don't know, 1/3, 1/3, and I see that elephants are being attacked under it. What that is going to tell me is that actually this whole region where I'm protecting gorillas with lower probability is just going to incentivize the attacker to attack elephants even more with more probability. So it's telling me that if I want to look for a better option, I should be trying to really increase slightly the amount of probability that I'm covering the elephants with. This is just a general idea. The fact that, one membership query, querying one point in the region is actually going to give us a lot of additional ideas about what's happening. This kind of looks like a binary search, in fact. There are ways to do this effectively and efficiently when we don't want to just do a repeated binary search, which is not very robust. In fact, the types of algorithms that are used here, without going into much detail, are about maybe optimizing a linear program using membership queries. Now, from your undergraduate education, hopefully you know that linear programs can be optimized having access to something called a separation oracle. Those are oracles that whenever you're out of the region will tell you that you're out and will provide you something that's separating you from the region you should be. Membership queries don't do that. They will just tell you whether you're in or out. They don't provide any line that would tell you that you're out. So how is this done? There are classical algorithms that use random walks. These random walks might look like something like this. I start with this strategy, and a random walk will just randomly start exploring and tells me what policies to design. And it might end up in a region that's actually not at all something I can even deploy. So a separation oracle would have given me this line, but the membership oracle is just telling me whether or not I'm in the region that elephants are being attacked. Now, I can also have another random walk, which while it's trying to figure out what's happening in presence of, in the region where elephants are being attacked, it might stumble upon another initial point that is where a strategy that gorillas are going to be attacked. So I could use that strategy now to actually do another type of random walk. So as you see, since each of these regions themselves are linear, and we know that random walks are actually quite effective in exploring linear regions, we can use random walks to find optimal policies within each of these regions. And we know that one of these optimal looking policies is exactly the right policy to incorporate. So this is a high level idea of how you could use these repeatedly, committing to one deployment and seeing what the attacker is doing to find out what's the optimal Stackelberg policy. If you do that, you can find a near optimal defender strategy that is learned by sort of adaptively trying out a number of deployments that are just polynomial in the number of targets you have. And then observing what the attacker is doing. This is nice because, the number of strategies that are available to the learner or to the defender could be much, much larger than the number of targets. So for example, it could be that, you have many resources and you can decide which one of them should go and protect the gorillas and which one of them should go and protect the elephants. But the fact that at the end of the day, the number of things you want to try out is just polynomial in the number of your targets is going to help. There's a question?
Yes, there's a question, and it's quite interesting. Eric asks, what happens if the follower knows that the leader is learning about them and intentionally makes a locally suboptimal decision to throw off the leader's attempt to learn their utility? It's an excellent question.
So that's a good question. So at the extreme when you are, let me just clarify one thing. In Stackelberg games, the reason that you can perform better than Nash equilibria is because you can reliably commit to a strategy. The basically follower believes that that's the strategy you're going to play for the rest of the time. So this kind of question that you're saying is basically saying, what if the attacker knows that I'm not committing? So that is actually at the extreme, as if the attacker is infinitely patient, it doesn't really care what it's doing, it just wants, wait around, is taking away your power of commitment. And that's where, instead of thinking, that's actually where Stackelberg equilibria, instead of being Stackelberg, becomes a Nash equilibria now in a general sum problem. So the notion of this completely changes if you're basically dealing with attackers that are infinitely patient. But the question that you're asking hasn't been answered fully yet. This is actually a very interesting area of research. People have thought about different versions of this, like what if the attacker, has a couple steps that it can wait around, or maybe it just doesn't want to have a bad deployment the next time around. So there are versions of this that have some positive answers, but in general, it's an interesting question that should be really looked at in more details. Any other questions? Okay. Cool. So that was for really offline learnability. Offline, not in the sense of pack learning, but as I was talking about briefly yesterday, when you can actually design the thing you want and see what happens to it. So those were called membership query learnings. Okay, so now what happens in repeated Stackelberg games? This was what Chara was talking about. And repeated Stackelberg games basically in this space means that you have multiple different types of attackers. And you're dealing basically with a sequence of attackers that each of these attackers has its own type of utility. So you can think about it as, maybe poachers who already have their hands in ivory markets, so they can draw a lot more money from attacking elephants, versus poachers that are actually mostly after the meat of wild animals, and they might actually prefer to attack gorillas even more so. So what happens basically when we're dealing with these multiple types of attackers, and we don't know necessarily the next day which one of them you're going to be facing. So that's the type of online learning that you can think about. In this setting, we basically need to assume that we know attacker types. We just don't know, which one is coming the next day. And we might have many different attacker types with different utilities. Importantly, the defender's utility is actually the same in all of these. It really doesn't matter. But the part of the table, which is the attackers, is what's going to define the best response. And that best response function, that RT, is actually what's changing based on which type of attacker we see. And just to repeat, the average Stackelberg regret is now, what our algorithm is receiving by, deploying PT and then seeing the response to that, versus deploying the best P and seeing the response to that best C. So that is just a, as Chara described, the Stackelberg regret that we are going to be working with. Okay, so what's one way of thinking about this? Take all the attacker types that I talked about and how, they divided the region based on what they were going to attack. And let's combine all of them into, one picture. Basically, this picture is telling us that within each of these regions, the attacker's best response, the vector of attacker best response, basically is remaining the same. And the kind of easy way to think about this is that just as our utility function was linear in each of the regions in previous ones, it's still linear now in each of these sub-regions now. And that's just coming from the linearity of what we have on the left and the fact that we have divided the space so that the response of the attacker doesn't change within each region. We can actually be a little bit more formal and try to understand that utility. So if I think of this utility as a function of two things, what number of times do I see each type? So Qj is just a number of times that I see an attacker of type J. And this vector Bi is telling me that within each region, who is going to attack what target. So let me just describe what this Bi is looking like. So if I look in the middle region, this vector is telling me that the first player is not attacking gorilla. The first player is not attacking a gorilla. The first player is actually attacking elephants. The second player is attacking gorillas. And the third player is also attacking elephants. So this is basically saying who is best responding. And what the utility ends up looking like is that within a region, basically, I'm taking this utility that would be drawn from having that coverage vector P when attacker is attacking target I, then times, what's the likelihood that target I is going to be attacked? It's the likelihood that, a type J is appearing and whether or not J within that region would be attacking I. So this is just a little bit expanded version of writing this utility so that it's kind of more clear that it's going to be linear. The second part, this U of Pi, this is just the expectation of the utilities. So this is just linear in the coverage probability as we discussed at the beginning. And this first part, these are just constants that don't at all depend on the strategy that you have deployed. It doesn't matter at all what P was. So these are not going to actually affect your utility at a higher order. So totally, if I look at this offline utility, it's linear in P. Chara, was there a question for me?
Yeah, there's a question. Nusha asks, does that mean that attackers have a probability distribution and one of them will be chosen? Or are we going to observe a random/adversarial permutation of them?
So you can think about as adversarial, not necessarily even permutation, because permutation means that, each one of them came once. I don't even know what's the distribution, like what the frequencies are. So I'm going to just, every day a new attacker is going to come. I don't know which one is more likely to come. It's just an adversarial sequence. Any other questions? Okay, so this is just kind of trying to understand the utility function a little bit more. How can we use the utility functions to kind of design an online algorithm? So in a way, if I'm in what we call full information setting, as in after one target is attacked, I know who the attacker was. Whether or not I caught them, I know which type of attacker was there. That's for us the equivalent of full information, because by knowing the type of attacker, we can actually compute the losses that we could have received from every option possible. So in a way, what we are going to do is, since our function is linear in each of these subregions, let's just try to learn about each of these subregions separately and mix that all together. So one way to do this is in a way to have an online algorithm for each of these regions and then combine their advice together with another meta online algorithm. That also works, but let me give you a little bit, a type of algorithm that is less efficient but easier to understand. So how would you do this? Remember that our utilities are linear in each of these regions. So if I just committed to what the best response is going to look like, my optimal strategy would be one of the corners, because linear functions are optimized at extreme points only. So let me just compute all of these extreme points that I know one of my best, one of the, the offline optimal is going to be one of these. So why don't I just like commit to these and only ever, try one of these extreme points. Now I'm going to perform online learning with these extreme points as the options that I have. So every day I have to decide which of these, probability vectors would be what I'm going to actually play around. So if you do that, because the number of extreme points, even though it could be exponential, once you apply the typical online learning bounds that were logarithmically in the number of options that were available to you, you still get a Stackelberg regret that is going to be square root of t linear in the number of targets and logarithmic in the number of types that is available to you. So this is kind of just like plugging in the previous bounds that you have seen and ignoring efficiency. For those of you who were here yesterday, I talked about the D structure that existed in auctions. For fun, you can actually go and try to see if Stackelberg games, the way I'm defining them, have a D structure for a small d, and you will find that they do. So, but we're not going to talk about the efficiency of them right now. So this is basically saying in the full information setting, it's actually quite simple to have an online algorithm to compete with the best strategy in hindsight, even if you have a sequence of adversarially selected attackers coming in. What happens what happens when we do not see the types? So let's say that maybe some attack happens. I know that a gorilla was attacked or an elephant was attacked, but I actually have no idea who the attacker was. I didn't catch them maybe, or I don't know if they're fit within a specific type. So if I can't see them, and the only thing that I'm seeing is what action was taken rather than who took it, what can I do? Well, this is somewhat between Bandit and non-full information. So how is that between them? In the sense that typical Bandit feedback will tell you that you see the utility of the option that was taken. So that would be basically the utility of you playing PT and the response to that PT. But right now I'm saying that, and sort of in that Bandit setting, if you went with that Bandit setting, remember that you would get average regret that is linear in the number of options available to you, which is the number of extreme points, and there could be many of them. And the reason sort of the typical XP3 algorithm that I was describing yesterday has this high of a regret is that it tries to build an unbiased estimator for each of these utilities, each of them, for each of the points, in fact, it's trying to build an unbiased estimator. And because of that, because it's trying to build a lot of unbiased estimators for different extreme points, it's as if it's trying to sample them individually, and it's doing a lot of rounds of exploration and not exploiting enough. And that's why the regret is so high if I were to just plug in a typical Bandit algorithm that I described yesterday. But in this case, we have more information than Bandit. In a sense, I'm seeing the response. And because I'm seeing the response, maybe I can do better. Why should I be able to do better? At a high level, let's go back to the utility that I described just a couple minutes ago. As I said, it's linear. And if I look at it again, sort of this, who is attacking what is something in each region. It's something I know. how much utility I can draw once I'm in a region, I know. It's a linear function of my utilities. I know all of that. The only thing that's unknown is actually, sorry, the frequency of each attacker type. The number of times that I see type, attacker type J arriving is something I don't know. And there are only K missing pieces, There are only K frequencies, K being the number of attacker types that I don't know. So how can I estimate all of that? So the idea is that you want to build a low variance estimator for these type frequencies by sampling only a few random points. And you want to basically explore these strategies that would choose those strategies that reveal the most about which agent type came and attacked. At a high level, let me build these vectors that say who attacked what animal within each of these subregions. In a way, what I am after is to understand each of, what's the likelihood of types 1, 2, 3 using, the likelihood of one of these targets being attacked. So in a way, what I'm looking for is really to come up with a linear basis of size K to figure out, what's the likelihood of each attacker type. Let's just see an example. For example, the likelihood of attacker type 1 is the number of times I see a gorilla being attacked when I use something in this region 1, minus number of times that I see a gorilla being attacked when I see something in region, when I place something in region 2. It's just because their vector is 1, 1, 0, 0, 1, 0 is going to add up to 1, 0, 0, which is the utility, which signifies probability of attacker type 1. Okay, now not every basis is made equally. Some bases will actually have much higher variance. So if I have a basis that basically takes 100 times one of them minus 99 times the other one, that could have a lot of variance. But if it's just one of them plus another one, that's going to have a much smaller variance because I didn't blow it up. So in fact, there are these bases called barycentric bases that make sure that you can still span linearly what you're looking at, but the linear combinations are just using bases that are like plus minus 1 or plus minus 2. So they keep the variance to be quite low, and they work really well when you're trying to come up with low variance unbiased estimators for online learning. So putting all of this together, you basically start with your extreme points. But instead of using XP3 on them, you choose a subset of them that form these barycentric bases. And then in XP3, instead of uniformly sampling all of the extreme points, you only uniformly sample or explore from the barycentric bases. If you put all of this together, the bound that you get is something like t to the 2/3 and nk to the 1/3. Let me just highlight something that I see. I have not a typo, but an inconsistency. I'm talking about average regret sometimes, where I'm dividing the regret by t. But in this slide, I'm noticing that I'm talking about total regret, which has not been divided by t. So when you go back to these slides, just have that in mind, which one of them has to be divided by the other one, by t. So this is the overall result I wanted to talk about. Just to wrap up, what you should take from this is that the structure of Stackelberg games, when we were in the security setting, and in particular the fact that they were linear payoffs, allowed us to explore the strategy space effectively, to divide the space to small chunks where we knew how to deal with them. And this really allowed us to both have offline and online learning in Stackelberg games pretty effectively. So that's what I wanted to talk about. If there are any questions, I will take them, while Chara, you can switch to your slides.
I don't see any questions in the Q&A.
I don't see either.
Should we just wait like 30 seconds more, or
it's
should
okay.
I start?
I think we can address them at the end of the session, so
okay.
we have enough time to cover what we want to cover.
Okay. So now that we talked about learning in Stackelberg security games, I'm going to spend some time talking to you about something that has drawn a lot of attention, both from the game theoretic leg of this literature, and also from the fairness leg of this literature, and especially the setting of strategic classification that we briefly touched upon yesterday as one of our examples for the admissions process. Now, I'll start by giving you some points about the game theoretic perspective, and I'll end with also perspectives that have to do with the fairness and beyond. So in this, when we're modeling strategic classification as a repeated Stackelberg game, what we are doing is the following. We're saying that for each round, T in capital T, the environment chooses the features from a set script X. And these features, you can imagine them as being the features of the student that is trying to get classified, get admitted to college. The learner, who is the particular college, commits to an action. So in our example, a classifier, we're gonna call them alpha T from a set of classifiers script A. Now the agent, who is the student, observes the classifier alpha T and his ground truth data point. So this data point is comprised by the features that the student has, like for example, the SAT scores that they had, the grades that they had from high school, and an input YT. What is YT? YT is the quote unquote ground truth label for that student, meaning that if the student were to actually report XT, what would a perfect classifier label that data point or that student? And we assume that for the sake of modeling that such a perfect classifier exists, but no algorithm that I know of in this space assumes access to this classifier. Yes, Nika?
Sorry.
Oh, okay. Okay, so the agent, oh, and I'd like to point out that at this point, the learner does not know sigma T, okay? So they just know the alpha T that they committed to. Now the agent reports to the learner RT of alpha T. This is the best response according to an underlying utility model that they have. And remember, as we talked about in the slide right before the break, this utility function is not known, and that's similar to what Nika was considering in the learning Stackelberg security games. The utility is not known. You only get to observe as a learner the response of the agent. So for example, this is the altered, like these are the SAT scores after you've taken tutoring classes, or you've taken SAT multiple times. The learner observes the label of this data point. Again, imagine that they have access to a perfect classifier, but just the label, not actually the classifier. You treat the classifier as a black box, and incurs binary classification loss. So this binary thing is just for the next slide. In general, you can incur any type of classification loss L that depends on the action that you committed and the best response of the agent that you saw at this round. And so there have been, as I said previously, two legs in this type of literature. On the one hand, people think of the game theoretic perspective, where the final label has to be equal to the original label, meaning that when you best respond as the agent, when you alter your data point, you are always unable of changing the ground truth of the data point, or you don't want to. And why is this assumption, this modeling assumption valid in a game theoretic setting? Well, because this setting is mostly motivated by spamming emails, where if you're a spammer and you see the classifier that an email provider has, then you will change your email just so that you pass the classifier to be non-spam, but you still are a spammer. You get no utility for being a good citizen and changing your email from a non-spam, to a non-spam. So this is the game theoretic motivation. And on the other hand, we have a second version where people take a more fairness-oriented perspective, And by changing your report, you might actually change your outcome. And this is especially pertinent in the schools admission example, where there might be mechanisms or algorithms that when the student gets to observe them and best responds according to them, then they can actually become better students. They can make their outcomes better. This is what we called yesterday using strategic learning as a societal force for good. And we're going to talk a bit more about that in the last slide, when I'm going to give you more open directions and the most recent literature around these things. So I'd just like to briefly mention, to touch upon something that I find quite interesting. Nika, when she was talking to us about the learning in Stackelberg security games, at the heart of her argument was a very nice geometric interpretation of the space. And that is so critical in learning in Stackelberg security games. And one might think that dealing with such geometric problems might just be contrived to learning in Stackelberg security games. Well, I'm here to tell you that that's definitely not the case. So there's great value when you're trying to actually learn the loss function as a function of the action that you play. There is great value in you understanding the geometric problem that lies behind the strategic problem that you have at hand. And here's an example. So in this paper that we wrote with Yiling Chen and Yang Liu, we assumed that here's the binary loss that I had from before. And we said that the agent's utility, despite that I don't know the utility exactly, I know that the agents can misreport in a ball of radius delta. So why is that a valid assumption? Well, remember that as we had in the example for the school's admission process, maybe this delta can encode your ability to misreport. It can encode your ability to pay for tutoring classes, or it can encode the number of times that you can actually sit through the SAT. So after you've done as big of a manipulation as you can in order to pass the classifier, this is what the delta encodes. And we are taking a game theoretic perspective again. So we are focusing on the case where you cannot alter your your ground truth outcome by misreporting. And here's why this gives you a nice perspective. In the next 2 slides, I'm going to explain you this. So from the agent's perspective and the learner's perspective, there's an information mismatch, should I say. So the agent gets to observe their true feature vector, and they get to see where exactly they can move. And once the learner commits to a classifier, then the agent can misreport something that makes them look good in terms of the classifier. Now, what does the classifier know by knowing that the agent reports in a ball of radius delta? They know that xt, the true feature vector, is lying somewhere around this region, but they cannot pinpoint exactly where xt lies, with the actual data point. But here's what they do know, and where this nice geometry comes into play. They do know that if they work in an augmented ball of radius 2 delta, they are guaranteed that they have captured all the potential positions of manipulation. And this means that if you have other classifiers, like for example, this classifier gamma or this classifier beta, these classifiers will never be manipulated by the agents, by the particular agent that you saw at this particular round. And why is that? Because they're farther away from the 2 delta power that the classifier, that the agent has. And very briefly, I'd like to tell you that touching upon why is geometry so important. It's important because you can actually translate that into the learner's dual space. Why? Because the learner's actions that are away, that are 2 delta away from the agent's data point, always satisfy either one of the 2 properties that you see here in blue and pink, which means that just when you observe the YT, the label of the data point, then you can actually infer your loss function for different actions, which in principle and as an idea and intuition is similar to what Nika was doing in the papers that she presented before, when she was trying to extract extra information while having very minimal information due to the strategic nature of people. And why am I saying that working in the dual space is so critical? I'm saying it because in the dual space, which is the learner space, each of the learner's data actions translate into single data points. So like this is a linear hyperplane encoded in terms of its normal vectors. And the regions that the blue and the pink create are actually regions that form polytopes in the learner's action space. And you can, similarly to what was the intuition that Nika showed, then you have actually a problem that looks like a more standard online learning problem, and you can try to build upon the standard online learning tools for different types of optimization. And this is what I briefly will talk about as the adaptive discretization as the learner's action space, which was actually able to give us a regret guarantee that was data dependent and dependent on the sequence of data points that we see. So contrary to the settings that Nika showed here, in strategic classification, we might go arbitrarily bad. So if the sequence of agents that we see are like arbitrarily bad for us, then we might end up incurring very bad regret. But if the sequence of data points is well behaving, then our regret guarantees are very good. And that is actually, and we can chat about that more afterwards, but I'd like to go to the open directions. This is actually something that's not just inherent in strategic learning settings. That's also something that is known in the offline learning world for learning linear classifiers. So just some open questions in this space, in the space of strategic classification in general. So learning against delta bounded agents is one type of utility, and there have been other types of utilities that have been studied, but we don't know what we can do, if anything, if we do not know this delta, or if people do not best respond. They just are what we call bounded, they have bounded rationality. So they do not always maximize their utility, but they report something that's close to what maximized their utility. Now, another very interesting direction that I'd like to see more work on is building data sets for strategic classification. So yes, we do use all of these examples for the school's admissions process, but we really have not been able so far to collect strategic data sets. And the problem is that we never know the ground truth labels. But I hope that in controlled experiments like in MTurk or controlled probability field experiments, we would be able to construct data sets for strategic classification. There's also a great space for work beyond linearity and classification. So like, let's work with classifiers that are non-linear, or let's move away from classification. What about clustering or other ML algorithms that are deployed in real life decision making? And just a slide about the themes for the research new directions. Again, Nika did not have time to touch upon that, but there has been actually work done in Stackelberg security games with bounded rationality or different utility models for attackers. There was also a question that was asked in the Q&A. Very recently, there's a paper that I actually co-authored with Akshay Krishnamurti and Theodoris Likouris, where we are able to achieve good regret guarantees for completely irrational agents. And why do these settings matter? Because think about a simple example in dynamic pricing, where you want to find the best price for this drum here in the 0-1 interval. The agent's true value is this blue line, but it's unclear, you don't know it. So you post this price here, the red price, and the agent tells you that, no, I'm not gonna buy because they are irrational. If they were rational, they would buy because the price is below their true value. So if they were rational, you would keep the orange space, but now that they are completely irrational, they do not buy. So you end up keeping just this small space here, which might result in huge revenue losses that are very important in OR-related settings. So in this paper with Akshay and Theodoris, we showed that there can be a bridge between incentive-aware learning and fully adversarial machine learning settings through the model of corruptions. And this means that the learning performance of your algorithms by using this bridge goes down as the irrationalities increase. And interestingly, this model can protect Stackelberg security games against irrationalities too. Finally, excellent work. I cannot stress this enough about the effects of strategic manipulation, both long-term and also short-term. What is the effect of randomness and noise in strategic classification, or how you can incentivize effort exertion from students. And finally, I'm very excited about this theme that's actually emerging right now about causality in strategic classification and what changes, how can you make your classifiers adapt better to agents that change their actual outcomes as a result of your classifier. So that was all for me, and I'd be very happy to take any questions that you have.